Now we're going to take a look at horizontal stretches and compressions. Start by identifying that parent function. So we've got the square root of x. Remember, that's half the sideways parabola. Have that picture in your mind before you graph it. The transformation on this one is a horizontal compression with a scale factor of 1/4. So when we set up our t-charts, we'll be multiplying the x values by 1/4. One thing you can do to make this easier, i.e. have fewer fractions, is to change your parent function x values to numbers that are multiples of 4. So I think I'm going to do that on this one. Critical point, still 0, 0. Multiplying by 1/4 doesn't change that. Domain, what's under the radical must be greater than or equal to 0. So x has to be greater than or equal to 0. And because there's no shift, our range is y is greater than or equal to 0. And because it's the square root function, I don't want negatives, so I'm going to completely change these x values. We're going to start with, I'm going to use the perfect squares on this one because it doesn't really work to make them multiples of 4, then my y values would be messy decimals. And the square root of these. So now I'm going to multiply my x values by 1/4 because it's a horizontal compression. So of course my 0 stays 0. 9/4 would be 2 1/4. Make it easier to plot if it's a mixed number. And the y values stay the same because I don't have any y stretches or compressions. And then we plot our points. So our critical point was still 0, 0. And in this case, I'm going to call each of these 1. So I'm using, again, these values from my t-chart. So over 1/4, up 1, right 1, up 2. Oops, sorry, that's 2. My scaling is off. Over 2 1/4, up 3, and then 4, 4. So we've got this horizontally compressed square root function. It's hard to see it because of the way that I scaled this graph, that it was squashed horizontally. But if you think about kind of taking your hands and pushing the graph that way, you can see that it did get closer to the y-axis, which is what happens with a horizontal compression. Step function. I actually really like the step functions for stretching and compressing because what it does is it changes the size of the step, so it's actually really easy to see the stretch and compression on this one. So we've got, again, our parent function is our step function. And we're multiplying by 1/2 in the asylum, so that means it's actually a horizontal stretch by a factor of 2. So that means that each step in our step function will be twice as long as it would have been from the parent function. No critical point on the step function. Domain, you can still round all numbers. And because it's a horizontal stretch, we're not shifting it at all. The range is still going to be that set of integers. So no shifting on this one, so we're still going to start at 0, 0 with that closed circle. And I'm going to call each of these 2 this time. And the bar will get twice as long. We're stretching it horizontally. So instead of a step of unit 1, it's a step of unit 2. There was no vertical stretch, so it's still going to go up 1 when I plot my next bar. I have to make sure I'm thinking carefully about how I scaled my graph. So it should be twice as long horizontally, but still have that 1 unit vertically in between your bars. And this one I could keep graphing for you, but I think you guys have the idea now.